So let me give you another different problem. We want to connect 4 cities with roads, A, B, C, D. So we want to be able to get from any one city to any other city. So there are lots of different paths. And the question is, which one's the shortest path? You can do this, but it requires more than calculus. It's called the calculus of variations. And it's a very difficult problem. But here's the answer. That's the shortest road surface from A to B to C to D. And maybe you would guess that, maybe you didn't. But here's a way to figure it out. You know you can set the length of the 2 paths in terms of the length, width, and height, and take the derivative and set it equal to 0, and that will give you the point. But there's another way. Those soap bubbles know so much. This is an experiment that was done where they looked at the city of Tokyo, and they said, let's connect parts of the city of Tokyo, and this is what the mold did in the replica, and this is what the Tokyo network of trains did. And Alfred North Whitehead said, seek simplicity. Got it. And distrust it. To tell my students on the first day of physics class, 100 students in front of me, half of what I'm going to teach you this year is true and half is false. And they said, why are you teaching us the false stuff? I said, we don't know which is the false stuff. And they said, but don't teach it to us. I said, no, we don't know which is true and which is not true. They said, but why are you going to teach us stuff that's not true? I said, because we don't know. They could not get the idea of the tenuous nature of science. I guess the one I like the best is when I ask people, is the Earth flat? Most people say, no, the Earth is round. And I'd say, okay. But the best answer I ever heard was, is the Earth flat? It used to be. So how did the light find the distance in the least time from A to B when hitting the mirror? How did it find it when going from air to water? How did it find it in the soap bubble? How does it find it to make a spherical Earth? Could these all be connected somehow? Is there an underlying theme to this? That's the beauty of physics. One explanation, least action for everything we know.
Good evening, everybody. I'm Sudhish, and I work for the Azim Premji Foundation. A very warm welcome to all of you on behalf of Azim Premji University. We are delighted to be presenting today's program in our series of public lectures here in Bangalore. This is perhaps the 83rd or the 84th since we started these lectures about 10 years ago. This is the second this year, in 2024, the first having been held in Indore just last week. We have a good crowd today, and I know many of you have come from far. Thank you very much. Public lectures are one of the ways by which the Azim Premji Foundation promotes its vision of a just, equitable, humane, and sustainable society. We invite public intellectuals from all walks of life to speak from this platform. So we've had Professor Manjul Bhargava of Princeton, we have had Joseph Stiglitz from Columbia, and now we have also Arthur. Arthur is not new to Bangalore. He's probably delivered 6 or 7 lectures already in Bangalore. And next month he will be followed by Michael Spence, the Nobel laureate in economics from NYU. A bit about the program this evening. Soon after this introduction, Dr. Eisenkraft will deliver his talk for about an hour. This will be followed by an audience Q&A, and my colleague Giri will close the session with a vote of thanks. We hope to close at 6 p.m. A brief introduction to Arthur. Arthur's CV was part of the invitation, so I'll just pick the highlights. He is the Distinguished Professor of Science Education and the Director of the Center of Science and Math in Context. Science and Math in Context is cosmic, very appropriately named, at the University of Massachusetts in Boston. Very many rewards and awards have come his way, including the National Science Board's Public Service Award, the American Association of Physics Teachers, AAPT's Millikan Medal, and the National Science Teaching Association's Carlton Award. Dr. Eisenkraft will deliver his talk on the nature of motion, a lazy or very efficient universe. Please join me in welcoming Arthur Eisenkraft.
Let's start by taking something which we all are very familiar with, the circle. And I was asking people, how do you describe a circle? And the answer is this. That's a circle. That's a good definition. Do you have a definition of a circle? What's a circle?
Well, the main standard definition is a set of points which are all equidistant from the center.
A very formal definition. And in fact, here it is, the locus of points equidistant from a given point. But we can move ahead, or we can do it experimentally by taking a string and wrapping the string around, and we see a circle. But how about this? Let's take a loop of string of fixed length. And with a loop of string of fixed length, I can make a triangle, I can make a rectangle, a triangle, a pentagon. I can make this unusual shape. But if I keep trying every shape, when I find the shape with the biggest enclosed area, that's a circle. And so the question is, which explanation do you prefer of these explanations? Do you prefer the largest area? That's toughest to prove, but you can prove it, and more abstract. It's not obvious, and it's somewhat intriguing. How does it become the biggest area? How do we prove that of all the possible shapes? So it turns out 2,000 years ago, Queen Dido played a little trick. They said she could have a city, she could have a location to live in, but she could take one animal hide and enclose the area with one animal hide. That's all the land she gets. And what she did was she cut it into tiny, tiny strips and made a semicircle and then put it on the coast. And that became the big area, much bigger than they expected Carthage to ever be. So we have different approaches, different solutions for identical problem. We have different models for the same phenomena. And one of the questions which we struggle with is, how do we support different perspectives from students during classroom instruction? So you're all familiar with the Necker cube. We call it a cube, but in fact it's just 12 lines. And yet with those 12 lines, right away, our perception, we say, no, it's a cube. But what kind of cube is it? Is it a cube like the blue one, which, and you're looking at it up and to the right, or is it the red cube where you're looking at down and to the left? Which is the correct way of seeing the Necker cube? We learn that light travels in straight lines. And so here we have light reflecting off a mirror. And people would like to explain why light travels in straight lines, how light reflects off a mirror. Here's some evidence that light travels in straight lines, which we knew way before lasers. Now, to understand how light travels with mirrors, we have to understand how we even see things in mirrors. So how do we see things that are there? Well, to see things that are there, we have a light source, and it hits the object, and then rays of light come off the object and hit your eye. Your eye then says, where are those light rays coming from? And you see the object. That also allows us to see things that aren't there. So here we have the light source, and it hits this part of the blue box, which sends light rays here, but they reflect off the mirror symmetrically like we saw. And now our eye knows that light travels in straight lines, which says, oh, there's another box behind the mirror. And we come up with a rule that the angle in and the angle out have to be symmetric, or the angle of incidence equals the angle of reflection. So we seem to like that idea. The light comes down, it hits the mirror, it goes up, it's symmetrical. But Fermat in the 1600s came up with a very different idea. He said, you know, the light can go from A to B many, many different ways. It can go from A to B along path 1, or path 2, or path 3, or path 4 or 5. But in fact, the way we see it go is path 3, the way we see it in the picture here. And Fermat said, that's because it finds the path of least distance. Out of all these distances, the path of least distance is number 3. But then, do you like the idea of the angle of incidence equals the angle of reflection? What I'm saying is light goes beep, 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 bounces off, beep, 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 beep. Or do you like this idea that it looks at all the paths and finds the one of least distance? Which is more compelling for you? So let me give you a different problem. This is a math problem. We have a room, And the room's dimensions are 5 by 10 by 15. And a snail is limited to the walls of the room. And has to get from one corner of the room to the other corner of the room, walking along the walls. So, the snail would like to take the shortest path between one corner and the other corner. So how does the snail find the shortest path? Well, it can do it by trial and error. We can mathematically measure this path. We can try another one. We can try another one. We can try all these different paths. If you know calculus, you know you can set the length of the two paths in terms of the length, width, and height, and take the derivative and set it equal to 0, and that will give you the point. But there's another way. If you open up the wall, then you just draw the diagonal, and it shows you where the crossover point is. So, which do you prefer? I prefer trial and error, that's a 1. I prefer the calculus, that's a 2. I prefer opening the wall, that's a 3. Which one do you like? So I see some 3s. Oh, people like opening the wall. A lot of 3s, not everybody's voting. You can vote, 1, 2, or 3. So everybody likes this opening the wall. So let me tell you what happens. Sometimes in school, what happens is the teacher says opening the wall is wrong. You have to do it the way it's in the book. The book says trial and error or calculus. Opening the wall is not allowed. And it bothers us to hear that, and we say, why would a teacher say this is wrong? And that's what we worry about. Why is it a problem for the teacher to say it's wrong? Why do some teachers do it? How can we support those teachers so they don't do it? And how can we protect students if the teachers do it? So let me tell you a more complex problem, one that's not as easy. You can't just open the wall on this one. What if one wall was sticky? What that means is, what if you go to this corner to that corner, but the snail can travel fast on this wall and slow on this wall? Where's the crossover point now? Because you want to go more on the fast and less on the slow. And mathematically, this is a very difficult problem. But we have help from nature. You see, light doesn't always travel in a straight line. You can see in the pencil or in the magnifying glass that light bends when it goes from water to air or from glass to air. So we can look at light and study light going from air to water. When we do that, we get what's called the law of refraction, and it has some signs in there and stuff, and it's called Snell's law. Fermat said, you know what? The path it takes, the path in red here, this path, which adheres to Snell's law, is the path of shortest time of all the possible paths. If light wants to get from A to B, and it could take any of these paths, it takes this one because that's the shortest time. So, let me try to explain how we know that's the shortest path, or how we can find it, or why it would be that way. You see, the example that's usually given is A is a lifeguard on the sand, on the land, and a B is a person drowning in the water. So the lifeguard has to help the person, and he could just make a straight line, but we know we walk much faster than people swim. If you've ever seen somebody in a swimming pool, the coach is just walking along saying, swim harder, swim, swim harder. It's so much easier to walk than it is to swim. So you don't want to spend a little time in air and a lot of time in the water because you're so slow this way. And you certainly don't want to spend a lot of time in land and a lot of time in water. So you keep trying these paths until you find one, more time in air, less time in water. And that gives you the shortest time, which is Snell's law, which is the path the light takes. So if one wall is sticky and you want to find the answer, just shine light on the open wall and it will bend at the point where it's the shortest time. and the shortest path. Now, which do you prefer? That light moves along here and then bends, or that it looks for the shortest time in order to get the correct path? Oh, so beautiful soap bubbles. Why do they form those spheres? It's the least surface area. Of all the shapes the soap bubbles could be, the least surface area is the sphere. So let me give you another different problem, a geometry problem. We want to connect 4 cities with roads, A, B, C, D. So we want to be able to get from any one city to any other city. So you could build a square, 4 roads, and then you can get from one city to another. Or you could have 2 diagonals, and you get from one city to the other. Or actually, you could go just this path to this and over. You don't even need the D to C, because to get from C to D, you just have to go the long way around. So there are lots of different paths you can do. And the question is, which one's the shortest path? And this one is very nice, but you could also move this up here, and then it becomes a little easier to get from C to D. 2 diagonals, maybe a circle. What's the shortest path? You can do this, but it requires more than calculus. It's called the calculus of variations, and it's a very difficult problem. But here's the answer. That's the shortest road surface, from A to B to C to D. And maybe you would guess that, maybe you didn't. But here's a way to figure it out. If you take a piece of plexiglass and you put 4 nails in the plexiglass, A, B, C, D, and then you put another piece of plexiglass on top of that. So you have a sandwich, plexiglass, nails, plexiglass. And you dip that in soap solution. That's how the soap forms, the least path. No calculus of variations. It just figures it out. And it can do that for 3 cities, 4 cities, 5, 6, whatever. It always finds the shortest path. Those soap bubbles know so much. And then we have a biological example that is way beyond my understanding, but we have slime mold. And when slime mold goes from one place to another, it finds the shortest path. So this is an experiment that was done where they looked at the city of Tokyo and they said, let's connect parts of the city of Tokyo, and this is what the mold did in the replica, and this is what the Tokyo network of trains did. And they did this for Roman roads in Central Europe and came up with the same solution the Romans came up with after a lot of consideration. And I think you have IKEA in India also. It's very hard to find your way out of IKEA. But they made a replica of IKEA, and the slime mold found the way out. So is that biology related to this physics of least time, least path? So let's go to some physics examples now. Constant velocity, motion. Over here we have a strobe picture. This is as if the object is moving to the right, and we only look at it every second. So where do we see it? We see it here, then here, then here, then here, then here. And we can see it's going at constant speed because they're equal distances. The orange is going faster because in 1 second it's from here, then it's here, then it's here, it's here. So we can see which one's going faster with a strobe picture. We have a strobe picture of a real ballerina here moving across. And we have another way of doing it, which is vectors, which can tell me with the size of the arrow how fast something's moving. And we actually have ways of depicting motion in graphics so that dance can be communicated from one choreographer to the dancers. Now, we also have graphs. So here, this is the location, and if you go like this, oh, you're never changing the location. You're always here at position 5, 5, 5, 5, 5, 5. You never, as time goes on, you don't move. While here, you go from 0 to 1, 2, 3, 4, 5. You're moving in a constant motion. And we also have poetry. Lewis Carroll wrote, "Flushed with new life, the crowd flows back again, and all is tangled talk and mazy motion, much like a waving field of golden grain on a tempestuous ocean." So we have poetry. Lots of ways to describe motion. But they only describe motion and not the why of motion, not what causes the motion. For that, we have to turn to Isaac Newton, who said an object in motion stays in motion unless acted upon by a force. If an object is going at constant speed, no problem. As soon as it changes speed, Newton says you better look for a force. If it slows down, speeds up, there's a force somewhere. You have to find it. That's what Newton's second law tells us. So we have one description of motion having to do with force. Sometime later, we came up with a whole different interpretation. We said, no. There's something related to the speed called kinetic energy. Energy, what is that? Well, maybe next year's talk. But energy is a number we can come up with. And you want to get that number for motion? You take 1/2, you multiply it by the mass of the object moving, you multiply it by the velocity squared, and we say that that number has to stay the same. It has to be conserved, unless it gets transformed to another kind of energy or transferred to another thing. So here I have lots of different motions. Let's look at the blue one. Constant speed. This is the speed. It's going at 5, 5, 5, 5, 5. Here it is. As the time goes, 1, 2, 3, 4, 5, 6, 7, the distance is now 35. It went 5, 5, 5, 5, 5, and it went 35 meters. But there's another way it could have gone from here to there and gone 35 meters. It could have gone 0, then went 2, 4, 5, 6, 7, 8, and got increasing speed. Or it could have started fast and go slowly. Or it could have gone fast, up to 10, then slowly. And in all of the cases, it's 35 meters. But if we take the mv squared and we look at this, and each time we calculate the mv squared, we multiply it by the time difference. So here, the v squared is 25, 25, 25, 20. It adds up to 175. For this other motion where it gets faster and faster, the kinetic energy is 245, the sum of the kinetic energies. If we go this way, it's 245, here it's 249. And which motion does an object move? Oh, we know. It moves at constant velocity. There's no force. That's only one way of looking at it. Another way is to say the sum of the kinetic energies, which we call the action, is the least. If you find the least action, that's the way nature goes. That's why it goes at a constant speed, because the action is least. Not because of forces, not because of cause and effect. So, which of these appeals to you? Do you like forces or kinetic energy over time is least? Why does one appeal to you more than another? So now we move to something more complex. This is an object falling. And you can see from the strobe picture that it's going very slow here because it only goes a little distance. Then it's going very fast here. It goes a big distance. So the object goes faster and faster and faster. And in fact, the speed increases over time. And we can calculate the distance it travels by looking at how much time has elapsed and squaring it. Now, for Galileo, the first person to ever do this, it took him 20 years to figure out you could give numbers to the motion, and then you could write an equation which would predict where it would be if you knew the time, and it turned out to be the time squared. 20 years for Galileo to figure this out. When we teach physics, introductory physics, we spend 10 minutes on this and say, it's so obvious. So here's a graphical model. The position changes, the velocity gets bigger and bigger, the acceleration stays the same. Another way to describe it. And we can describe it with force. In fact, that's what Newton did. Newton said there must be an attractive force between the sun and the planets. Everybody was worried about this. Why are the planets going around the sun? What's going on? Where is the force? And Newton went further than just the sun and the planets. He said, oh, an apple falls to the earth and moon falls to the earth, and they all work the same way. And then he went even further and said, an apple and an apple attract one another. And everybody said, what? He said, no, just like the moon is attracted to the earth and the earth is attracted to the sun, apples and apples attract one another. But we can't measure that. Just trust me, we can't measure that. We'll never be able to measure that. It's okay, 100 years later they measured it. So, but this idea that the sun and the earth attract each other, or even that if I take a pen and I let it go, it knows which way to go. How does it know which way the earth is? How does it communicate? How does the earth communicate to the moon? And when they asked Newton, he said, yeah, I don't know. I don't make those hypotheses. Hypothesis non-fingo. So, another way of looking at that, not forces, is energy. So we have kinetic energy as 1/2 mv squared. But if the object is coming down, the kinetic energy is very little. Then it gets bigger and bigger and bigger. But you just got done telling me kinetic energy is conserved. So it's like, oh yeah. Well, I said, the rule is energy is conserved. And kinetic energy obviously is not, because it gets bigger, 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 bigger. So there must be another energy that gets smaller, 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 smaller. And we give that energy a name, gravitational potential energy, GPE. And if you add up this one and that one, it always stays the same. And so here, I have a little toy. So I take the toy, and maybe I have to go down here to do this. And I can give it some spring energy by compressing it, and I can let it go, and it gets kinetic energy going up, and then it gets potential energy and stops. I can do that one more time. So I just take it, and I push it down, and whoops, and it goes up like that. It's okay. So if I look at the energy, that's great. If I look at the energy here, what's happening is it starts off with a lot of spring potential energy and no kinetic energy or gravitational potential energy because it's at the bottom. Then when it leaves the table, it has a lot of kinetic energy, but it's still low. Then when it gets to the top, it has a lot of gravitational potential energy and no kinetic energy, and the spring energy is gone. But if I add those up, the sum is always the same. The kinetic energy plus the GPE plus the spring potential energy is a constant. So that's our energy explanation for objects coming down. Kinetic energy and GPE is constant. Okay, so what we have for the falling apple, if that was an apple, the apple falls to the ground. Well, it doesn't really fall to the ground. It falls toward the center of the earth. The ground happens to be in the way. Gravity pulls the apple down. Well, not quite. A force pulls the apple down. We just give that force a name and call it gravity. Well, actually, the force pulls the earth and the apple together, but the earth doesn't move very much. The apple, another explanation, the apple and the earth have gravitational potential energy. The apple falls and the GPE of the apple, earth, decreases while the kinetic energy of the apple, earth increases. And we have conservation of energy. So all of these work. Now, I am so confident of these rules that I'm willing to risk 50 rupees that Galileo was right. That if you take the time squared, you'll know the distance it falls. But this is the beauty of the base of physics that Galileo taught us. Find a phenomena, make measurements, describe it mathematically, basically, is there an equation, and then use the mathematics to make predictions and check to see if the predictions are correct. So I have 50 rupees, and I'll have my colleague here do it, because then he might even give it back to me if he wins. So come over here. What I'm going to do is I'm just going to take the 50 rupees, and I'm going to fold them in half, like this. And it's very simple. You just have to go like this and catch it. I'll let it go, and you just catch it. And if you catch it, you get the 50 rupees. Okay. But I don't want you to go like this. So if you could just put your arm like on the table so you can't move your arm down, we'll give it a try. Okay? You ready? Okay? So you know what, right? No, no.
Too fast.
What's too fast? You?
No.
No, the rupee. Yeah. So it's, oh, you want to be able to move your hand down. I say, oh, let me do it this way. So we do that, and then, no. So, yeah, I could have risked 500 rupees, but I've never done this before, so I wasn't sure. So I'm so confident because I know the length of a 50 rupee bill, and I also know how long it takes to fall, and I know what people's reaction time is. I had him use these fingers because he's much faster this way. So that was just an extra safety on my part. So these are all cause and effect. A force causes the motion. And I can graph this for you. I can show you how this works. Here's the time. 0 seconds, 0.1, 0.2, 0.3, all the way up to 2 seconds. And here's the position. It starts at 20, and it goes down to 0. And here's the speed, which I can calculate from this, and it's minus 0.5, minus 1.5. It's going faster and faster. We use negative numbers because we use positive for going on the way up, negative for on the way down. So what we have is, here's the position from 20, it goes down to 0, 0 position at the end of 2 seconds. And the speed goes from 0 down to minus 19.5 meters per second.
What's the last column?
These, this is over time. Yeah.
No, I couldn't see.
Okay. Yeah, it's small, and I have to get all those numbers in. It's hard. So what we have is that we have the gravitational energy, the kinetic energy. They must be constant. This works. Energy is just a way to count. Review the spreadsheet and display the graph with energy. And we did this. Oh, here it is. This is the the kinetic energy. Goes faster and faster and faster. This is the gravitational potential energy. I calculated that here, mgh. And that looked like that. And I added them up, and it always came out to be 200. The energy is conserved. What a nice picture. This is what we teach in school. Such a nice picture. This is a way to understand motion. But is there causality? We know the energy at the top. We know the energy at the bottom. We can calculate the speed at the bottom, but we didn't know why energy is conserved, or what is the underlying principle of physics. So let's go back. This is my object moving at constant speed. Beep, 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 beep. There was no change in gravitational potential energy because it was on the level table. Yes, energy was conserved, kinetic energy was constant, and we found a new quantity which said sum up the kinetic energy over time. We'll call that action, and it's the least action. And we did this, and we said, oh yeah, look at that. The action is 175. That's the path it'll take, constant speed. And that's the one nature does. Now, it could have moved many other ways, but it didn't. It moved the way that the sum of the kinetic energy over time was least. And energy is conserved, but we have this new quantity, because now we have gravitational potential energy, where we take, instead of adding up the energies, let's subtract them. Kinetic energy minus GPE, called the Lagrangian. And we can sum them up over time. Let's not worry about why. But we sum them up over time, and let's look at what happens. With the block moving at a constant speed, well, the gravitational potential energy was always 0, so it was straightforward. But with the object falling, we know the kinetic energy changes and the gravitational potential energy changes. And so this is one way in which an object can get from the top to the bottom. There are many other ways, an infinite number of other ways. It could go at a constant speed, just like the block moving across the table. It could go fast, slow, fast, slow, fast, slow. Just like, it could go fast, stop, and then keep going. It could go down and then up and then back down. There are so many ways for it to go from here to here and do this in the same amount of time. You have 2 seconds to get 20 meters down, and any way you want to go is okay with me. The way nature does it, or go fast and slow, go at a constant speed, go fast, slow, fast, slow, fast, slow, go down, up, down, up, down, as long as you get down in 20 meters in 2 seconds. The path, which has the least kinetic energy minus GPE, is the one with constant acceleration. It's the least action. It's the one nature does, out of all the possibilities. So here I have a chart. which shows you the time and the position and the velocity. I calculated the kinetic energy and the GPE, but instead of adding them, I subtracted them, multiplied them by the change in time, and the sum, the least action, was minus 123. So now let me try something different. Instead of the velocity getting bigger and bigger, let's have the velocity be constant, always minus 10. Now the action is 90. But minus 123 is less than minus 190, least action. Let's start off and have it go very fast, then stop, then go fast again, then stop again. The action now is 198. It's less than 123. And so here's a game. You put in any way you want it to move, whatever you think is the way it might want to move, and I will tell you that the sum is going to be never less than 123, minus 123. So how do you like this model, this least action model? The sum of Lagrangian over time. Nature looks at all the possible paths and chooses the least action? How? How does nature find the least action? When the apple falls, there are no forces. We're saying a different explanation. I don't want to hear about forces. Nature doesn't care about forces. I don't want to hear about causality. Forces cause motion. I don't want to hear about that. I don't want to hear about energy conservation. Oh, energy is conserved. Nope. All I care about is least action. Find the action of every possible path. The one that's the least is the way nature will move. So, how did the light find the distance in the least time from A to B when hitting the mirror? How did it find it when going from air to water? How did it find it in the soap bubble? How does it find it to make a spherical Earth? Could these all be connected somehow? Is there an underlying theme to this and connection? So, Occam, years ago, 2,000 years ago, said nature does nothing in vain, and complex is in vain when it can be simple. Aristotle said basically the same thing. Nature takes the easy way out. Newton's laws of reasoning, he has rules of reasoning, 4 rules of reasoning. And his first one is, we are to admit no more causes of natural things than such as are true and sufficient to explain their appearances. To this purpose, the philosophers say that nature does nothing in vain, and more is in vain when less will serve. For nature is pleased with simplicity and affects not the pomp of superfluous cases. Now, Newton thought that the simple explanation, when Newton was looking for simple, he said forces and motion, that's simple. But other people are saying least action is simple. So I keep saying, what does nature do? And it's quite presumptuous of any of us to say, what does nature do? And Fermat, the same Fermat, wrote this letter to a critic of his, and he said, I do not pretend, nor I've ever pretended to be, in the inner confidence of nature. She has obscure and hidden ways in which I have never undertaken to penetrate. I would only have offered her a little geometrical aid on the subject of refraction, since she should have been in need of it. But since you assure me, sir, that she can manage her affairs without it, I won't mention it again. So we like to say, how does nature do this? We can't. No, nature knows how to do it. We have to try to say, what's the simplest way that connects the most things so we understand how nature does it. Now, this would be a wonderful philosophy of life outside of physics. And Alfred North Whitehead said, seek simplicity. Got it. And distrust it in life. And H.L. Mencken, the journalist, said, for every complex problem, there is a simple solution. And really, there are so many problems in the world now. We worry about climate change. We worry about this. We worry about that. We worry about wars going on in the world. And you can speak to people and they say, oh, no, I know how to solve that. You know, they spent a half hour. We have people spending all the time thinking about this. They spent a half hour. I know the answer. And Mitchell Mencken said, for every complex problem, there is a simple solution. And it's wrong. And then Kahneman and Tversky won the Nobel Prize for what they called fast thinking and slow thinking. That sometimes we have to go with fast thinking, to get from here to the cross. I'm not going to calculate. I'm just going to go. I look for fast thinking for most decisions, but for some, I better slow down my thinking and look at all the alternatives if I want to make sense of the world. And what we try to teach our students is slow down your thinking. None of this science instruction is obvious. Don't go with your gut reaction. So again, all of these things, could they be connected? And the answer is yes. We found out in the 20th century how they were all connected. Feynman and Tominaga and Schwinger came up with quantum electrodynamics. And Feynman explains quantum electrodynamics by saying, yes, I know light travels from A to B. That's the shortest path. It travels in a straight line. But why doesn't it take other paths? When it goes off the mirror, how did it find the right path? How did it find the right way, the shortest? And what Feynman explains to us is the light goes in every path. The light takes every possible imagined path. So there is a beam of light that gets from A to B this way. But we don't see that because there's another beam of light which is so close to it, and those two beams cancel each other out. And so the only path which doesn't have a partner to cancel out is this one, which is the least time. And you say, you have evidence for this? Yes. There are ways to get rid of the orange path, and then you see the blue path, if you get rid of the pair. So Fermat's principal path is the shortest path. It's the least action path. And nature finds it by trying all the paths and finding it. So Ovid said, the cause is hidden, but the effect is known. It was with Fermat and light. It's less so with Feynman's quantum electrodynamics. So I told you what Galileo said science was: find phenomena, describe it mathematically. Is there an equation? Use the mathematics to make predictions, check to see if the predictions are correct. And then Feynman said, but the real glory of science is that we can find a way of thinking that the law is evidence and overwhelming in so many different areas. So soap films minimize their surface area. A large piece of matter maximize the gravitational attraction. Light rays bend and follow the path of least time. The orbits of the planets are those that minimize something called the action. The path that a relativistic particle follows between two events in space-time is the one that maximizes the time measured by a clock on the particle. So not everybody was using least time. So when Einstein came up with theories of special and general relativity, he came up with special relativity in 1905. In 1907 said, it's correct, it's wonderful, there's another way to get to your same result, Einstein, and that's using least action. When Einstein worked for another 10 years or 8 years on the field equations about gravity and general relativity, Hilbert said, yes, using your Riemannian geometry is a good way to do it, but if I use the principle of least action, I come up with the same equations. So we're back to this. Which do you prefer? What if the teacher said this was wrong? What would a teacher say? Why would a teacher say it's wrong? So how do we support different perspectives from students during classroom instruction? So we've learned there are multiple routes to the same destination on a map. We all know that. There are multiple scientific models to explain the same phenomena, as I was trying to show you today. And as teachers, we try to guide students to the right model, to a good model, to a model that will give them confidence. And we're not sure if one model is better than another model. So many of you are probably familiar with Gauss. When Gauss was in 3rd grade, The teacher needed some time, and they all had their chalkboards in front of them. And what happened is all the students were told, please add up the numbers from 1 to 100. You've learned addition, so now add up all the numbers from 1 to 100. 1 plus 2 plus 3 plus 4 plus 5 plus 6. And the teacher expected this would take some time. Gauss came up right away and said, it's 5,050. And Gauss is a brilliant mathematician and physicist. And how did Gauss do that? He said, quite simply, 1 plus 99 is 100. 2 plus 98 is 100. 3 plus 97 is 100. There are 49 of those. That's 4,900. Then you have a 50 in the middle and 100 at the end. 5,050. Now, what if if Gauss's teacher told him, no, that's not allowed. You have to do it the way it's done in the book. And it's horrifying for us to think of that might happen. But it happens every day. It happens every day where a teacher says, no, you have to do it the way the book says, or the way I say. So those are the questions. Why is it a problem? Why do teachers do it? How can we support teachers so that they don't do it? And how can we protect students if the teachers do it? So why is it problematic? You get that gut sense, what a terrible thing to tell this student, to tell Gauss. So we know it stifles creativity, it reduces critical thinking, it creates a fear of making mistakes. It's limited understanding of the nature of science. It undermines confidence. So why would a teacher do that? The teachers are trying so hard to teach well. Why would a teacher do that? And we can try to figure this out, and if we were having a seminar, we could sit down and not look at a few answers I came up with, but I would say, why do you think teachers do? And I think we'd come up with all the answers, that they're nervous, they don't know the content themselves, so let's do it the book way. Or they've always done it this way, so they feel confident with the way the book does it. Or class management. No, we're all going to do it the same way. It'll avoid confusion because Gauss is trying to explain this and other kids can't even add 1 plus 2 plus 3. So there are lots of reasons why teachers try to do this. On the standardized exam, they want them to do it this way. No creativity on your standardized exams. We don't want creativity there. So what do we do to support teachers? Well, the Azim Premji Foundation is spending a great deal of effort working with teachers across the country to try to get them to better understand how we approach it, how do we approach right answers, how we approach wrong answers, how we approach different alternatives. So we have professional development workshops, collaborative planning sessions, promote inquiry-based learning, a different way of teaching. And then we need, for teachers who haven't figured this out yet, who do this to a student, we have to protect our students from these teachers. So parent advocacy, peer support, a group study session of students. It might be college students, not third grade students. This professor will have to do it his way, but there are other ways to do it. Open dialogue, awareness, student-led initiatives, clubs, ways to say like, let's have a club and we'll explore other ways to do things, even if we can't in class. We know if we do this in science, we'll miss discoveries, bias in research. If science people, no, we have an explanation, leave me alone with your new explanation. That's not the way it progresses. I tried a couple of times, a couple of years in a row, to tell my students on the first day of physics class, 100 students in front of me, half of what I'm going to teach you this year is true and half is false. And they said, why are you teaching us the false stuff? I said, we don't know which is the false stuff. And they said, but don't teach it to us. I said, no, we don't know which is true and which is not true. They said, but why are you going to teach us stuff that's not true? I said, because we don't know. They could not get the idea of the tenuous nature of science. And in fact, recently, the editor of Nature magazine, one of the foremost science publications in the world, was asked, so how many of the articles that you're publishing today do you think will be overturned? And I thought he would say 10%, 20%. He said, all of them. Just think. Just think about how the ideas change and how we have to respect that, and we have to respect student views. I guess the one I like the best is when I ask people, is the earth flat? Most people say, no, the earth is round. And I'd say, okay, but the best answer I ever heard was, is the earth flat? It used to be. There was a time when everybody in the world agreed the earth was flat. And they had evidence. They just went outside. It's flat. And people laugh and they say, yeah, but we know it's round because we're so smart. They were stupid. How do you know in 300 years people are going to say, round? Are you kidding? They really thought that? Oh, no, we know. We don't know. We only think we know. So we want to respect students' views. We want them to do that. It supports their emotional development. It does this, it does that. We want to respect people's way of looking at the world. And I was at the market once. I don't know if you use these units. I'm not sure. Do you use, this is a long time ago, but I wanted to buy a seher of ghee at the market. Do you have a seher? Is that a unit of ghee? One seher is, okay. So I wanted to buy one seher of ghee. That's what the units were. And it was, what was it? It was 11 rupees a seher. And I said, how much do you, I want to have a seher. He said, I don't have a seher. I said, how much do you have? He said, I have 9/16 of a seher. And I said, okay, I'll take it all. How much is it? And I take out my pen, and I take out my paper, and I go, 9/16 of 11 rupees, I do the math, I know exactly how much it should cost. He told me, exactly. And then I said, how did you do this? I need paper, I need this, I have to do multiplication, He said, oh, well, there are 16 anna in a rupee, so he did it in base 16, it worked perfectly. But I had to respect this person who had no education at all and got the right answer, that he had a way to do this. So how do we choose one model after another? Accuracy, simplicity, elegance, utility. Why do you like that opening the wall so much? Herman Weil said, in my work, I always try to unite the true with the beautiful. He's a mathematical physicist. But when I had to choose one or the other, I usually chose I chose the true or the beautiful. Let me see with your fingers. What a group. Yes, he said the beautiful. He said, now, when you're really attuned, when you're very good, and you choose the beautiful, as he did, as Faraday did, as Einstein did, it turns out the beautiful turns out to be the true. We started out with the circle. Find the shape of the biggest enclosed area. That's the circle, not this, not just this. We had the Necker cube, two different ways of looking at it. We had the light reflecting off a mirror, different ways of looking at it. We had this opening up the wall as a different way to do it. We had the apple falling and least action as a new way of looking at it. But least action works for all of them. So in the Gita, Krishna says, have other eyes, new light, and look, this is my glory unveiled to mortal sight. Maybe he was thinking about least action. So the principle of least action I could touch on here. It works in light. It works in objects moving. It works in electricity and magnetism. It works in special relativity and general relativity. It works in quantum mechanics. It works in everything and provides to understanding that's the beauty of physics. One explanation, least action for everything we know. William Bragg said, the most important thing in science is not so much to obtain new facts as to discover new ways of thinking about them. Albert Einstein said, we cannot solve our problem with the same thinking we used when we created them. They're all moving toward, we need new explanations. We get there by respecting our student scientists. Oh yeah, I don't call my students science students. I call them student scientists. Because science student, okay. Student scientist, oh, I feel good. You can just feel this, like, oh, I'm more special now. It's such an easy saying. And there are ideas we expect scientists to find original and better ways of understanding nature. Thank you.
So, can we not say that there is an intelligent field that solves all the problem? It is the supreme boss of all the fields, comprising of the Higgs field that gives mass, the electromagnetic field that gives light, the gravitational field that gives influence, the proto-consciousness field that provides consciousness, and the information field that tells what is mass or density or what in the world is going on.
Yes, we can. That's even simpler because it not only takes into account all of physics, but all of humanities and history and everything. The question we have in science, not in these other fields. And of course, what are you going to call this present being? Are you going to call it God or are you going to call it nature? You know, but here's what we do in science. That is a question. That explanation, oh, why did this happen? The being made it happen. Why did that happen? The being made it happen. Why do I do this? The being makes that happen. Can you now predict something that I don't know about? And then we can look to see if that turns out to be true. If you can't do that, we have no use for your theory. Theories in science allow us to make predictions about the future, and when we look to that future, we say, it's right. We have no way to test whether it could be right, but we have no way to test it. So it's not a part of science. But it is a part of feeling comfortable in the world, and I recommend it.
Yeah, so I have a couple questions. The first one is that you said that the principle of least action holds across a lot of processes in physics. The way it works out in light is that light travels in every possible path from point A to B, and all the paths that can cancel out, they do cancel out. But that is not the case in the case of a falling object or an object moving at a constant velocity. Then there is only one object and there's nothing canceling out. So how does the principle of least action hold there?
So it's a very good question, and I don't know if I know the answer to that. If it was a particle moving, it would take all paths. So when do you go from this quantum mechanical view of tiny particles, light, electrons, protons, to massive objects? And how do you make that transition? That's a wonderful exploration that people have, is semi-classical physics. When do you make that transition from one to the other? But the one question I have based on your question is, but we know the object doesn't do that. And how do you know that? We see the one path, but how do you know there aren't other paths that we don't see? But, oh no, I'm sure there aren't other paths. So that's the other question, is there something that's hidden from us that might? But the real question is, what happens from quantum mechanics to classical mechanics, that transition? When do we make these changes? What happens? Why do the laws change? We know that the laws of quantum mechanics can explain the macroscopic behavior. We know it doesn't work the other way. So we build up. But that's certainly, but the least action works for the object, but the mechanism for the least action, yeah, I'm not sure.
My other question is that you said that we can observe the principle of least action if we subtract GPE from KE, right? And it's always the minimum. But isn't that partly because of the convention of what we label negative and positive? If we switch that around, wouldn't then it become the principle of most action?
So that would be interesting. And just to a small correction, it's the kinetic energy minus the gravitational energy integrated over time, multiplied by time. Okay, that's the one. No. I mean, would it be the biggest number? I'm not sure. But that's the way it's defined. And also, we can take kinetic energy minus GPE integrated over time and show that's equivalent to Newton's laws, while the other one is not. So there are ways to go from this least action to show, well, why does Newton's laws work so well? Why does conservation work so well? And we can get from there to there when we define least action, the Lagrangian, as the kinetic energy minus the GP and not vice versa. So, such good questions.
Thank you very much. I really enjoyed the lecture. As someone who didn't like physics in high school and college, I didn't have good teachers. But the latter part of your presentation really resonated because I am an educator myself. So my question to you is, given the systemic issues we have in the education system, both here and in the US, with several challenges, how do you inculcate that spirit of inquiry and, really maintain everything that you described while dealing with so many systemic challenges? How do you remain a passionate and committed educator to your students?
So are you asking how we inculcate that with our students or with our teachers?
Both.
Why not? Why not both?
In a system that fails us a lot
yeah.
of times.
So I'm glad that the questions about education that I raised resonated with you and you're giving it some thought, and that's what we all have to do is give it some thought. I think that teachers need evidence that this other way is going to be better for the students and also better for them, that the classes become more exciting and engaging for them and for the students. But there are real hurdles. None of us like to change. And we have veteran teachers who have taught for some time, and they say, I'm successful, and sometimes they have good evidence for their success, and sometimes they have very weak evidence for their success. I've met a teacher who's like, oh no, I'm a very good teacher. How do you know? Oh, 4 years ago, one of my students got into the top university. And what about your other 400 students? Well, no, this student got into the top university. I must have been doing a good job. So we have that issue. But also, we're asking teachers to take 2 steps back and do a lot of work with the promise that we'll take 5 steps forward. I think all of us who are educators know how all of us as people know, it's like, wait, you want me to take 2 steps back? So how many people are familiar with the Rubik's Cube with those colored sides and you keep moving it? So no, not many people? Yes, okay. So the Rubik's Cube, you get the 6 sides and you have to get it so you have the red, the yellow, the blue on each side. And when you first play with this, you go, and then you finally get the yellow side and it's right, but none of the other sides are right. And then it's like, you have to get rid of the yellow side to get 2 sides. I don't want to get rid of the yellow side. I finally, and then you do it, and then you have 2 sides, but it doesn't, it's like, no, now you have to get rid of both of those. And it's like, you know what, I'm happy enough. And so that happens with teaching. So I think the idea is to recognize that teachers want to do their job well. They want to engage the students. The students want to do well in school. And we have to find ways to do that. And it's not to punish them or to have them stand up and say, this is not a good teacher, but to work with them and to, in small steps, show, why don't you try this and then tell me how that worked for you. Yeah. It's my struggle.
So there was this question on why the ball doesn't go like this, or why it doesn't go like this. So I think the answer is everything has some wave-like properties, and it depends on its mass. So if the mass is really small, it'll have a lot of wave-like properties. It'll be much more quantum-like, and it's like an inverse proportionality. So if the mass is large, there'll be very small wave-like properties, right? And so for everything, the ball can go like this. There's just because of its mass, there's a very, very low chance of that happening. A ball can tunnel through that, but there's a very low chance of that happening. And the smaller you go, the higher the chance it becomes. And if you throw a ball like that really fast, it's going to go. Quantum electrodynamics. But it needs to be a really quantum for a higher chance. But the ball has a lot more mass than those particles, right? So it's a bit rarer to see a ball just flying away when you throw it down than it is to see a photon flying away. And it won't fly away. These photons and all particles want to travel in straight lines because they want the maximum lifespan.
Thank you. It's a wonderful question. And the only reason I hesitated was when you said, like I want to have a good dinner tonight. They want to do something. We have to be careful about that in science.
All right.
But your question is very
So-
good. And please.
No, it's not a
let
question.
Let me give
I'm
a
trying
chance to respond
answer.
to your question.
I'm trying to answer. So everything goes in a straight line to maximize its lifespan.
It's
So-
lifespan.
Yeah, because of relativity, right?
Okay. So now it's my turn? All right. So this is a wonderful question with a wonderful, important background. It turns out you're asking almost the same question that this gentleman asked. He said, when do you go from quantum mechanical to classical? And you're saying, wait, if the mass is small, it's quantum mechanical, then when the mass gets bigger, something else happens. And you're telling me about probabilities of going through walls, tunneling through walls. And the question is, can we calculate those probabilities? And you say, it's very small. How small? So what we want to do is we want to take these explanations, which you have, which you feel comfortable with, and now put numbers to them so you can understand it even better. And then you'll say, it's this big a particle. But the only issue I had was when you said, they want to. Remember, because I almost said the same thing. How does nature do it? It's like, no, we can't. If you want to know how it does it or what it wants, we have to go back to this gentleman's question. Thank you very much. No. We'll talk afterwards, okay?
Thank you so much. So you're mostly talking about pedagogical rigidity, right? In some pedagogical rigidity, right? Like the way things are taught,
Yeah.
right? Mm-hmm. So just to give a light anecdote, right? Like I teach my son mathematics, right? And he's a young kid, he does addition, 2-digit addition. I teach him the repetitive, every day you do it. Some days he's reluctant, and yesterday I was giving him a problem, and he didn't want to do it, but he remembered that 2 days ago, I gave the same two numbers, right? Like he just looked up, and that is the principle of least action there, right? But joking aside, right? The way Newton's laws are taught, or F equals ma, the equations we learn, they're not the most intuitive. They're not the right. There are simpler ways to teach things, right? But how much of it? Of this is because of historically, that's how it's been taught, right? Like probably from the 17th century onwards, textbooks have carried the same equations, and we just kind of continue to do that. And at Newton's time, it's probably also the variables that go into these equations are probably the easiest to measure, right? Like in some ways, right? Like distance and mass, and right. But now that this action is a little bit, it's different for every kind of problem, right? How do we define it? Now that we understand, and we are kind of able to minimize some other derivative or a property of these other variables, right? Like that's what you're heading towards, right? Mm-hmm. But essentially, for every one of these problems, there is a better way to teach it. Like there's something that's the simplest linear path from A to B. But that's not being taught in schools, right? Like that's is my point correct? Yeah.
So you've made a number of very interesting and informative points. The first is that you've told us all how fortunate your son is to have somebody whose parent can help him with math problems and give him math problems and support him. And we look at rural India and we say, they don't have parents who can do that. And that's already a disadvantage and a problem that as a nation, India has to look at, America has to look at and say, what are we doing to support all of our students? It's interesting. So then, yes, the equations are exactly the same. I have if I walk in the physics department at my university, I'm in the physics department, and there must be 30, 40 introductory physics textbooks. And they all say, I have a better way to teach it. I have a better way. Oh, no, let's do it this way, let's do it that way. But the equations better be the same equations. You know, it's very interesting. When I went for the first time to a history conference, and they read their paper word by word, philosophy conference, they read their paper in front of people, word by word. And at a physics conference, nobody reads there. But the graph and the equations, oh no, they're very careful about that. They don't fool around with that. It's not like, d equals 1/2 at squared. That might be 1 at cubed, I don't really know. No, we know. You know, so what's important in our field? And so we do that. The historical approach is one way to look at it, because we evolved through that. But sometimes, like, no, we don't teach the phlogiston theory of heat because we know it's a waste of time. Historically, it's interesting, but we don't need it. So, but what we struggle with is what is the best way to motivate students and have them learn the content and achieve well. So we just keep struggling with these different techniques, and you know, every once in a while somebody says, I have a better way to do it, and sometimes it really is a better way, and everybody says, yeah, let's do it that way now. But that's part of the struggle. I remember I was telling a group of students at Eisenkraft University yesterday, we were asking about, how do you evaluate students? How do you know if they understood you? If they understood the lesson, how do you know if students understood the lesson? When I was a young teacher, or a young supervisor of teachers, and I said to somebody, how do you know the students understood it? The teacher could say, I could see it in their eyes. And that was considered a good answer. Oh, okay, that's a good answer. And I was like, we don't accept that as evidence anymore. That's not, the field has moved forward. You know, something else besides you can see it in their eyes. So we do check for understanding and find new ways to do that. And you know, there are so many aspects to the content you're teaching, the way you teach it, and then the way you assess it, that all have to work together, and they all need improvements, and we can keep struggling with that.
Hello. Hi, Professor. Thanks very much for the talk. Quick question.
I can't. Oh,
Yeah,
thank you.
up here. Yes, I was watching a video where Professor Brian Greene and Mr. Eric Weinstein were talking together on the string theory piece, and the conversation was where Mr. Brian Greene talked about how elegant the theory of string theory was because it reproduced some of the quantum mechanical results as well. And I mean, I think feedback from the stage where Mr. Roger Penrose and also Mr. Eric Weinstein were on said that elegance can't maybe be a valid enough defense for a theory. Not that that is the only defense for string theory, but I was just curious on where you stood on that debate, because you also put in that quote about how it results if they were beautiful. Odds are that they're probably right. So
you know, there's an aesthetic of science, and some things we just say, oh my goodness, that's just so beautiful, and you just, you know, like the example for me is opening up the wall. It's like, why didn't I think of that? You know, so Brian Greene is talking about string theory and things like that. And the problem with string theory is elegant. The problem is that nobody knows how to test it. So we don't know if it's right or not, or what's the evidence. Now, again, Newton with the two apples, we didn't know how to do that, but Cavendish 120 years later said, wait, I can make that measurement, so in 120 years, maybe we'll be able to find out if string theory is right or wrong. But we don't want to take string theory on faith alone. It should predict something that we don't know to see if it happens. But I wish you know, simple, I mean, Einstein's theory of general relativity is incredibly complex mathematically, but it's beautiful. You know, so, and it's simple. It's so simple. Even though it's so complicated, it's such a simple way to look at so many different things. But I remember Einstein being asked, what if your theory of general relativity is wrong? And he said, then I feel sorry for God. And what he meant was, it was not sacrilegious, it was not, I don't believe, it was God didn't know to open up the wall. There was a better solution than the way he did it. This is better than the way he did it. And you know, we just keep finding better ways to do it. And when I go to a museum, an art museum, and I see a painting, and right away I know it's a Monet or a Cézanne or a Picasso, it's like, how do I know that? Because they all defined a way to look at the world, and we recognize that way of looking at the world. You hear a piece of music and you say, it's Mozart. Oh, I should tell you that story, because you would all know. I told to a few people here. So when I arrived here a week and a half ago, I was in Bombay. And I went to have a cup of tea. My flight was next day, a nice cup of tea at a nice restaurant. And I'm sitting there, and sitting next to me is an elderly woman, about 90 years old, with her son, I guess, or somebody younger. And we were all just having tea in the same place. But people are coming up to her, touching her feet, touching their head, and I said, okay, this is somebody, you know, they're not doing this with anybody else. What's going on? So when it came time to pay the bill, I said to the waiter, I said, who is this person that was sitting next to me? He said, oh, that's Asher Bosla. Asher Bosla. And I said, oh, who is that? And he told me, oh, she's a very famous singer. And I said, like the one who died last year? That's her sister. And then I went back to the internet and I saw how famous she was. And, but, you know, she defined a way of singing. You know, the quality of her voice, but it was more than the quality. There was probably something about it, you know she's singing. There's something she defined for the world. And for many generations, because yesterday again at the university when I'm dealing with 19-year-olds, and I mentioned the story, and they all, oh, really? And I said, wait, there are 75-year-olds who like her, 50-year-olds, 30-year-olds, 20-year-olds, everybody, the same singer. I couldn't think of another person like that in America who transcends generations, transcends all generations. So she must have done something to grab everybody's attention. And yeah, well, somebody told me a wonderful quote yesterday about defining the world. It was Einstein meeting Charlie Chaplin. You know this story? Okay, then I won't. I've never told it, so you'll have to correct me. So Einstein said to Chaplin, I'm so impressed by your work because you found a way that transcends cultures, that transcends language. You found a way that everybody can understand something, everybody. And it's so impressive. And Chaplin said to Einstein, well, I so admire you because you've done something that nobody understands. And we all still admire you. So, yes.
Can I? Yeah. Acha, is this applicable to movement of heat, conduction, convection?
I don't know, but I think probably yes. I'm sorry, I don't know.
Yeah. So, sir, I had a question and a comment. Question, I'll get it away because if I'm not able to frame it correctly. So, the action principle is a mathematical artifact, and if art means, is there any research going on the causality of action principle, why it is the way it is? Means, we observe numbers, it is minimum and this. So is there research around the why of the actional principle being there?
Yeah, no, I think it takes away causality. It's just a number. It's, you know, just like conservation of energy, which we all understand, is just a number that seems to always hold constant. If you add up these numbers, they always are the same. But there's no, this happens, then this happens, no.
And a comment was 5 years back, you had given a talk on motion on the moon, Bangalore only, football on the moon. There was a talk. So
Yeah.
after your class, I went back, I read the Quantunes magazine, and I did that Fermat principle in the class, even though it was not in the syllabus. And there was a really wow factor. Luckily, at that time, I was teaching both math and physics. And this year, I was very happy to see in the IB board, they scaffolded Fermat principle and included it in the math paper. So maybe the push to include it comes when a scaffolded question starts coming in the exam, then the administration and everyone will fall in, oh, marks, let's start teaching.
If we all get better, it would be wonderful. If we could all grow in our teaching as you did.
So, Professor, I want to ask you, how important is it to get students to also understand there are questions which science does not answer, does not claim to answer? For instance, nature, you said, follows the principle of least action. Nature likes simplicity. So if a student asks you, why does nature like simplicity? That you hit a dead end even in science, how important do you think it is to get students to understand that too?
Yeah. I think what we don't do a very good job of doing is helping students understand what is science, what is the principle of science, what is the domain of science, what is not the domain of science. And there are certain filters we have where if you ask me a question, I say, oh yeah, that's science. So for instance, if somebody were to go fishing and they go like this and the fishing line makes all kinds of shapes, that's very complex. But they said, can you explain that? It's like, well, I can't, but there are physics people who, that's a physics question. Well, how does the cord move? It moves by forces, it moves by energy, maybe even action, I don't know, but it moves. But if somebody were to ask me, what was Cézanne's influence on Picasso? I would say, that's a wonderful question. It's not science. And I know the difference. Do I communicate that to my students? What are science questions? What are not science questions? And that's part of, well, what does it mean? How do I know that difference? And does it meet the requirements of science? Does it, so there are a number of criteria that I've written about and stuff that you know, at least tests and things like that, what do we assume, and you know, what are the filters we have? It's just, it's such an interesting question. We have filters as adults, as people who are interested in science, because I guess you're all interested in science, and teaching because you're here. When students come up to me and they say, did you hear this? I sometimes say, oh, that's very interesting. No, I didn't hear that. Can you show me where you heard it or whatever? I'd like to read more about it. Other times students say, did you hear about this? And I say, no, it's not true. And they say, no, it's true. I say, wait, is it a movie? Is this a TV? Was this, you know, no, I don't believe you. I just don't believe you. And why don't we believe that student? So I'll give you an example. I gave this the other day. So one of my examples. So you must have some Bollywood magazine, like we have People magazine, and they're probably 100 pages long, and you buy them weekly at the supermarket or whatever, at the market. So somebody comes up to me and says, did you see People magazine this week? And I said, no. They said, it's 15,000 pages long. I say, no, it's not. I don't believe you. They say, no, I saw it. It's 15,000. I said, I don't believe you. Because I'm doing a calculation saying 15,000 pages, 500 pages in a book, 30 books. No, they could not deliver this to my house. You know, it's just not possible. I don't believe you. So I have a detector. I have a filter system that says, I don't believe you. You know, and I'm certainly have no expertise in biology, but if somebody said, I heard a woman gave birth to a porpoise, I would say, no, I don't believe it. The little biology I know says, not going to happen. So do we have that filter system? So there are a whole bunch of things we have. I like to call them crap detectors. Critical, CR, analysis A of physics. See, critical analysis of crap. Do we have a crap detector which tells us, don't trust this, trust this? And that's what it's about.
What I want to ask is, Bill McKibben said, at the core somehow, when we are addressing climate change, is the question whether the big brain we have compared to other organisms, was a good adaptation. When I see around in nature, trees, animals, they all follow the principle of least action, so to say. They survive, and it's all been good for perhaps millions of years. Is it because of our excessive action and a bigger brain that we land into this soup, which I don't think we'll come out of?
So in biology and the creatures and how they came to be, we have a different theory called the theory of evolution, which explains this very well, how they came to be the most efficient or for their environment at that time. What's happening in the world and individual people is so much more complex than any physics I know, and certainly I can't touch upon what's happening.
Thank you very much, Arthur.
Thank you, Gary.
Thank you very much to the wonderful audience, because every time an author is here, if it's such a wonderful evening, I think it's because of this very, very engaged audience. Thank you very much once again for coming over.
Thank you.